In this tutorial, we're going to start talking about how we can plot directivities, and we will start with 2D directivity patterns. And at first, we need to decide which angles we are going to plot over. So to define the angles to plot over, we're going to use the Numpy Linspace. We can decide to use angles in degrees, or we can decide to use angles in radians, or we can decide to use both. Later on in other tutorials, we are going to take a look at some classes and functions we are going to use to plot these directivities, and we're going to see that they accept both degrees or radians. So there is a flag. In case of, for example, the cardioid family, we have here these degrees, and we can turn it to true or false depending if we want to use degrees or radians. And we also have this get response from this directivity object that we created using this cardioid family class. We can get a response, and we also can set this flag degrees to true or false. So if we set degrees to true, that means that we're going to use degrees, and if we set it to false, then we are going to use radians. So the first thing what we need to do is to define the angles that we're going to plot over. So we want to see how the directivity works, in this case in 2D. So we are in the XY plane, and we want to see the directivity over the full 360 degrees in this plane. So let's remove this and put it in a separate cell just for convenience. So here we are defining the angles to plot over. We are going to use the Numpy Linspace function, and it's very convenient if we decide to use angles in degrees for now, because we can easily use increments of 1 degree. So we can go from 0 to 360 degrees in increments of 1 degree, and we will have information from degree 0, 1, 2, 3, and so on until we reach 360. But we could also use radians, and we could go from 0 to 2 pi, but then we need to define the number of points that we want in this linear space. And then when we use from 0 to 2 pi, it's not so easy to get the number of points to use. Like when we use degrees, we can have increments of 1. This linear space function, it takes integer as this number of points inside this interval. And if we would decide to use the from 0 to 2 pi, and we can decide some number of values inside this range from 0 to 2 pi. For example, here it's commented out, but we can use 1000 points, 100 points. We need to check what is more convenient for us. So let's take a look at what Numpy Linspace does. This is a very widely used function that returns evenly spaced numbers over a specified interval. So returns the num evenly spaced samples calculated over the interval from start to stop. The end point of the interval can optionally be excluded. So it takes as parameters the starting value of the sequence, the end value of the sequence, unless end point is set to false, and then in that case the sequence consists of all but the last of num plus 1 evenly spaced samples, so that stop is excluded. We have this num, that is the number of samples to generate. It defaults to 50, and it must be non-negative. And we have a boolean, that's the endpoint. It's an option parameter. If it's true, stop is the last sample. Otherwise, it's not going to be included. And as default, the endpoint is true. We can also have an axis as option. The axis in the result to store the samples. is relevant only if start or stop are array likes. This function will return the samples. So there are num equally spaced samples in the closed interval from start to stop, or the half open interval from start and stop, not including stop, depending on whether endpoint is true or false. There are other functions that also can generate some arrays that are similar to Linspace, but used a step size instead of the number of samples. We can use log space and so on. So in this case, we are going to use Linspace, and here we see that we don't give the step size of 1, of increments of 1, but we give the number of samples in the interval. So from 0 to 360, we have 361 values. 0 also counts as a value. And then we are choosing to have 361 samples in this interval with endpoint rules, so containing the 360 degrees. So let's print these angles. We'll see that we'll have values 0, 1, 2, 3, 4 until 360, and we will compute the directions for all these angles. We will plot the directions over all these angles. But okay, suppose we don't want to use the angles in degrees. Suppose we want to use angles in radians. So the concept is the same. So we will compute angles from 0 to 2 pi, and we will have 1000 samples in this array. And this is what we are going to do here. Let's print also these angles. So now we have values that goes from 0 until 2 pi, and 2 pi should be 6 point something, 6.28 around. But we could also generate the angles in degrees like we did before, and we can use a function that converts these degrees into radians. And in this case we would have, let's print also the angles now. Let's take this. So now we are generating angles in degrees with our Linspace, but we are converting angles to radians using this function Numpy radians. And we have also the last value is 2 pi, but now it's just taking all the degrees 0, 1, 2, 3 and converting to radians. So we can also use this approach. So let's see, when we plot, we will discuss this code in a different tutorial, but here we are going to use at first angles for the cardioid family class, so degrees are true, and we are going to use radians. As an example, let's use the angles in radians, but we are defining first a linear space with increments of 1 degree, so from 0 to 360 with 361 points, and then we are converting these degrees into radians. And here we are using degrees false and degrees false, so we are using radians. And when we run this, we have this nice plot with different patterns. We have the figure of 8, the hypercardioid, the cardioid, the subcardioid, and the omni. But now, suppose we want to not convert from the previously generated angles in degrees, but let's generate 1000 samples inside this interval from 0 to 2 pi. Let's see when we plot. So we're still with degrees equals to false. So we have also our nice plot with the directivities.